This is a droplet of tin, smaller than a strand of your hair. Every second, up to 100,000 droplets like it are blasted into plasma inside a machine that costs about $400 million. It weighs 180 tons. It holds more than 100,000 components, wired together with kilometers of cabling inside. Only about 300 of these systems exist on Earth. And every day, machines like this help print the chips that end up in phones, AI servers, electric vehicles, and the next generation of computers. Apple, NVIDIA, Tesla. Every major AI data center depends on chips made possible by this process. But here is the strange part. Physics was never supposed to make this easy. To understand why, we have to go inside a place the outside world is almost never allowed to enter. The air in this room is cleaner than a hospital operating room by tens of thousands of times. A single dust particle, smaller than a virus, can be enough to ruin a chip worth $50,000. Inside this room, a war is happening. The problem is here. To print the chip you use every day, ASML has to create a very unusual kind of light, EUV, at a wavelength of 13.5 nanometers. That is roughly 14 times shorter than ultraviolet light, closer to soft X-rays than to visible light. This kind of light is absorbed by almost everything: air, glass, human skin. Physics says no. Humans answer, there must be a way. The answer was not one invention. It was a machine that fights physics in almost every component. More than 100,000 parts, each one solving a problem that the universe does not want to solve. How do you create EUV light in the first place? How do you keep that light alive when every mirror absorbs part of the beam? After 6 mirrors, only about 12% of the original photons remain. 88% is lost to physics. How do you keep those mirrors clean while plasma is firing debris at them every second? If one battle is lost, a wafer worth hundreds of thousands of dollars can become scrap. If one machine goes down, $1 billion fab can stand still. And if the leading-edge chip supply chain slows down, a generation of AI systems can slip with it. So how do humans avoid losing? 6 stages, 6 battles. Each link in this chain is a place where physics can defeat human engineering. To build one of these machines, the supply chain stretches across continents. Mirrors from Germany, lasers from Germany. A light source first developed with roots in the United States. Final assembly in the Netherlands. Then shipment by multiple Boeing 747 cargo flights. Reassembly inside a customer fab, often in Asia. One machine, 4 continents. It can take about a year to ship and install, then months of testing before the machine prints its first production wafer. But before that moment, we have to go back to the first battle. It begins with one of the most ordinary metals you can imagine: tin, the same basic metal you find in canned food. It is melted at 232 degrees Celsius, then sprayed into droplets about 30 microns wide, 50,000 to 100,000 droplets per second. Imagine trying to hit a falling raindrop tens of thousands of times every second, where every miss means less light for the entire chip-making process. The timing has to land in microseconds. When the droplet reaches the focus point, it is hit not once, but twice by a laser. The first pulse flattens the droplet into a disc. The second pulse turns that disc into plasma, 220,000 degrees Celsius. The surface of the sun is about 5,500 degrees Celsius. This plasma is roughly 40 times hotter than the surface of the sunday, and humans create it up to 100,000 times every second. The plasma has created the light, but EUV light does not reflect on any ordinary mirror. So Carl Zeiss, in Oberkochen, Germany, built a new kind of mirror. Dozens of layers of molybdenum and silicon, stacked with atomic-level precision. A specialist at Zeiss might spend years, sometimes an entire career, on a single type of mirror. If one of these mirrors were scaled up to the size of Germany, the tallest mountain would be only about 1 millimeter high. Each mirror reflects only part of the light. After 6 mirrors, about 12% remains. The rest is lost to physics. And that remaining 12% has to print an entire chip. The light passes through something called a reticle. A reticle is the mask that holds the pattern of the chip you are going to use. Before it ever enters the machine, a technician in the mask shop inspects it for defects, because the pattern on that reticle becomes the pattern on the wafer. If the reticle is flawed, the printed chip is flawed. From there, projection optics shrink the pattern by 4 times and place it onto photoresist on the wafer. The result is a pattern smaller than a virus. The margin is so tiny that an error at the scale of atoms can help ruin the wafer. After a year of shipping and installation, months of assembly and testing, more than 30 years of EUV development, a machine that has consumed the work of thousands of engineers and the power of an entire industrial ecosystem, all of it converges at this moment. 30 years of questions reduced to 4 tests: resolution, overlay, throughput, defect rate. If even one test fails, ASML can miss milestone payments. A customer can delay a node ramp. Apple or Nvidia can delay a new chip launch. 1 year, more than 100,000 parts, $400 million. The final question is simple. Today, will physics surrender? Most smartphones made since 2024, modern laptops, new electric vehicles, AI data centers. Many of them rely on processor chips that passed through one of these EUV systems. One Dutch company makes the commercial EUV systems used in high-volume advanced chip production. One critical link. Without it, the leading edge of the chip industry slows to a crawl. About 300 machines, standing quietly, printing the chips that run the modern world, one wafer at a time. This is a droplet of tin. Each droplet is a small battle with physics. And that battle is how the smallest chips in the world get printed. Next time, we go inside the cleanest room on the planet, where a single speck of dust can destroy a chip worth $50,000. Beautiful as cinema, honest as documentation. That's Factory Story Lab. If there's a process you want us to explore next, let us know. Until then, trust the build.